Since you have been talking about a lot of superstructure stuff, I'm going to talk about the foundation, like in road pavement, the base or sub-base stuff. So let's go into the soil a little bit. This study is inspired by some field observations, so I'll try to talk about it as I go through it. And I'm going to look at just a little bit of background and then objectives, and then I'll discuss a new equipment that we developed to be able to study this topic, and then we'll discuss the results and then the possible applications. So how our pavement will behave will depend on the foundation, the base and the sub-base. And ideally, we will want to, if we get the opportunity, we will use the material that we meet in situ. But for most cases, those material don't have the specification or doesn't meet the specifications to be able to perform that function. So we either transport material from different sites, or we try to stabilize the material or improve the strength. Common practice is using cement or fly ash or other methods. Though this helps us be able to achieve some sort of improvement, it comes with some negative aspects where the material becomes very stiff, so it becomes susceptible to cracks. So how do we intervene to be able to minimize this crack? Can we do something about it? There's a benefit for sure, but if you're able to use the material we meet on site. For example, you wouldn't need to, like I mentioned, transport material over a long period, over long distances. The environment, to some extent, will be at least protected. In the US alone, about 1.2 billion tons of sand and gravel are used for construction, for different aspects of material use. So if you'll be able to improve the material we meet on site, for sure, we're able to save a lot of cost and also minimize time, cost in many ways, time, energy consumption, and even greenhouse gases emissions. So like I mentioned, this project was based on some field observation. What they did was a road that was constructed. They observed that a certain section developed cracks, much, or let's say, the intensity of the crack were more compared to other sections. Other sections even didn't develop crack at all. So they wanted to know why is it that for the same span of road, and then cracks are happening in certain sections. So they went back to the data that they collected during the construction phase, and they observed that the section that developed a large number of cracks during the construction phase, due to variability in construction processes, obtain the maximum moisture content, which is what we usually do. Traditionally, you want to get the optimum moisture content and the density in the field. But they observed that those sections that experience those maximum densities develop the highest crack. And the section that did not develop cracks achieve moisture content below the optimum. So the question was, why was it happening? And then can we now utilize this observation to our advantage? So what we propose, or our theory was that, is it possible that during the construction phase, we will provide moisture content which is lower than the optimum, and then later go back to kind of supplement by a second stage of moisture content. And our theory is that when you look at this figure, the black dashed line is the traditional mix where you supply optimum moisture content, and then the sample will develop the strength consistently. And then as the soil dries and achieves strength, the shrinkage stresses and strain that build in the sample as the soil becomes more stiffer. So we are saying that if you supply lesser moisture content, you minimize the amount of water available for evaporation, and therefore you minimize the shrinkage stress and strains. So during the second phase of moisture content, you'll be able to achieve higher strengths, whilst also minimizing the potential of shrinkage cracking. So this was the idea. So what we try to do is very simple. Can we use the sequential hydration approach, whereby you are supplying moisture content below the optimum, and then later add on moisture content? Can we minimize cracks? Can we achieve higher strength? So the test that we did was to do drying shrinkage test and then compression and direct shear test. So to be able to apply the sequential hydration, you have to develop this equipment, which help us be able to apply both positive and negative pressures, be able to measure volume change during the saturation process, and also measure humidity and temperature during the process. I'm not going to present a lot of data about the temperature and other stuff, just the mechanical aspect of what you observe. This is a very detailed stress path that we followed, but the important aspect of this slide is, simply put, we prepared a sample at a moisture content below the optimum, and then wanted to know on which day should you go and apply the second stage of the moisture content. Is it 2 days, 3 days, 7 days? So we studied 3 days in a 7-day period. So what we did was that we prepared 3 specimens. One of them has the optimum moisture content, and the other ones, we gave it 60% of the optimum, and the other one, 80% of the optimum. And then we wait for 3 days. For the optimum samples, we test them after 3 days. For the 60 and 80, we supplement to the optimum, and then we wait for 3 days, and then we test them. If you want more details after the presentation, we can discuss them. So this is what we observe for the shrinkage drying test. Let me say one more thing. For the shrinkage drying, we did 3 cycles. And for those one, we use kind of rectangular prism samples. And at each cycle, we dry the sample completely, and then we saturate it again, and we dry it. So a kind of cycle process. So this is what we observe. So we measured the shrinkage, the total shrinkage, and then I tried to convert it into the rate per hour. So this is what you observe. The sample that experience optimum moisture content, you realize that the rate of shrinkage drying is intense compared to the 80 and 70. Even for the first 10 days, what is surprising is I can see that the 80% moisture content show the least drying shrinkage, even compared to the 60. The same thing happened in the second cycle and in the third cycle. As you can see, all 3 cycles, the black line shows the least. So we measured over 30-day period. So we wanted to see that at the end of the 30 days, that's the maximum shrinkage that you can observe. How does it compare to the first cycle? And you can see that when you compare the first cycle to the second cycle, for the 100%, the first cycle is about 130% more than during the second cycle. And then all of them can see the first cycle shows the highest drying shrinkage. And it can be explained by this simple total strain equation. At the end of each drying process, and then we take it through the oven to dry it, the epsilon P component is the plastic strain. Usually it is irrecoverable. Once it is kind of, let's say the sample explains the plastic strain, it's unable to go back. You can only sustain the elastic strain. So at every cycle, you start with a total strain, which is the elastic and the plastic. At the end of the drying, the plastic strain is kind of irrecoverable. You can call it, you can assume. So what does this imply? It means that potentially there's an ongoing process, but what we observed so far, in terms of drying shrinkage, if you apply the moisture content below the optimum, there's a tendency that you'll be able to minimize the potential of shrinkage cracking. But then you try to continue to do, like I said, compression to see volume response and then direct shear parameters. So the compression response, for the first day that the sample was compacted, you observe that the volume change is dependent on the stress. You can see in the early part of the curve, everything seems to be together, and then they seem to separate as you increase the stress that you are using to compress the sample. And then after 3 days that we apply the sequential hydration for the sample, you can see the volume change response is more of the compaction-induced state, which is kind of the moisture content at which the sample was prepared. And then for the 7 days, it seems to be a couple effect of both the compaction-induced and then the stress influence. So now, shear strength, I'll continue on, and then later on, I'll discuss what is important about this volume change, which is the CC, that's the index, compressibility index. Now I'll discuss in the later slides. In terms of the shear strength, this is what we observe. For the 100%, we tested the stress between 50 and 200. And we observed that almost all of them followed a sort of contractive behavior. In other words, more contractive, at least between 50 and 150. And then dilative behavior, which is the red one, is only when we went above 150 kPa. But for the sequential samples, you can see just 50 and 100 show the contractive behavior, while the 150 and 200 show dilative behavior. And then one important thing that we observed that in terms of the maximum shear stress that we measured, shear stress, the sample that experienced the sequential hydration increased about 30% and 36% for those that were prepared with this 60 and then the 80% optimum moisture content. Now, the samples that were 3 days before the sequential hydration, this is for the optimum moisture content compared to the sequential hydration. Observation number 1, the optimum moisture content, they fail at a very lower shear displacement, or the horizontal displacement, a very, very low displacement. And also the value compared to, of course, compared to the sequential hydration, those ones fail at a much higher horizontal shear displacement. And also the maximum shear stress that was measured is higher for both the sequential hydration sample compared to the optimum moisture content. And the same as the first one, they increased about 30 to 36%. The 7-day sample shows similar trend compared to the optimum moisture content. But then the increase in the shear strength was about 45% as compared to the 36 that was measured. Now, when we measure the shear displacement, our interest as geotechnical engineer, we want to use the Tazaki samples, more column, and analyze it. But we are dealing with unsaturated soil. So the Tazaki equation has been extended to capture for unsaturated behavior, whereby this component is accounting for the suction component or the capillary effect. And then this is dependent on the normal stress, and this is dependent on increase in the internal friction level based on the suction that you have applied. So that's, but because I did not control this in the testing equipment, whatever cohesion that I'm measuring, we'll go this together with that, because we believe suction contribute to the kind of cohesion that you measure. So this is the shear envelope that the strength envelope that we measured. The 80 seems to show the highest, at least the friction angle compared to the 60 and then 100. But the most interesting thing is when you look at the sequential hydration sample, you can see on the 3 days, 7 days, the strength is quite significant compared to the optimum moisture content. So I estimated those parameters, like I mentioned, which is the CC, the friction angle, and the cohesion. And what we observe is that for the optimum moisture content, cohesion consistently decreased over the 3 and 7 days, whilst the sequential hydration samples cohesion kind of increases. In terms of friction angle, 80% seems to show a slight decrease in friction angle, and then the 100% or the optimum moisture content seems to show an increase in friction angle. Volume change, it seems the highest volume change is observed at least on the 3rd day of before sequential hydration. So to be able to visualize the impact of what the method that we studied, I calculated the percentage difference from day 1 and then compared to the 3 days and 7 days. And we observe that the highest volume change you observe on the 3 days if the sequential hydration is applied on the 3rd day. And then the implication that in the field, if you compare the sample and then we supply sequential hydration on the 3rd day and then compact again, we'll be able to achieve higher density. Number 2, cohesion was observed to increase of almost 1,000%. That means that the tendency for crack to happen has reduced significantly, because cohesion means there's a strong bonding, and then the potential for cracking will minimize. What we observe that may appear to be a bit detrimental is the decrease in the friction angle, which I'm postulating that is because of a decrease in the interparticle, the number of interparticles that is in contact, because if there's a high cohesion, all the particles are kind of together. So the surfaces of the number of particles that are sliding past each other per time is kind of minimized or restricted. So that will account for why we will experience the decrease in the friction angle. So the conclusion that we are making is that there is an ongoing studies, and this is the preliminary observation that we have found. We are trying to simulate an actual experiment where we can measure crack size and then depth and the pattern and all those kind of stuff. But for now, for the preliminary studies, one conclusion is that if we compare the sample at a moisture content lower than the optimum, and then we supplement it later on, there's a tendency to be able to decrease the potential of shrinkage cracking by a huge amount. And then in terms of the shear displacement, I mentioned that the sample deformed at a much higher horizontal displacement compared to the optimum moisture content, which means that there's a tendency for deformation. For example, samples that have been sequentially treated will be able to experience larger deformation before failure occurs. And then the friction angle, as I've already mentioned. So the practical implication, to summarize, is that we will be able to reduce the potential of shrinkage cracking if you apply the sequential hydration method. Thank you.
Thank you, Seth. Maybe time for one question.
Yeah. Go for it.
I have a question.
Sure.
So how did you affect clay?
Clay.
Yes. And also I see that
so let me start with the soil that I'm studying here it's not a clay sample though. It's a polygraded sand, which give me a second. Before I go directly to your question, I have the particle size distribution here. So it's a based on the CC value and then the particle size, we classify it to be polygraded sand. That's what we are dealing with. But clearly we have to apply surcharge, right? And wait for a period of time for water to drain and all those kind of stuff, right? Yes, C, but yes, I did, because when you apply the stress, of course, there was a drop in volume change. So you expect to compete for CC for sure, absolutely. And then what you observe that the sequential hydration sample, the third day seems to show the highest volume change. And I'm saying that we can use that to our benefit. It means that if we apply the sequential hydration on the third day, and then we compact our soil layer, we're able to achieve higher density in the field. Yeah.